Let's recap the nonparametric sign test for hypothesis testing about the median of a single population. Remember, with nonparametric techniques, we can't assume normality. Okay, so a parametric technique has the requirement that the population, or at least the sampling distribution, follow a normal distribution. If we can assume that, that is, if the population follows a normal distribution, or if the sample size is big enough such that we can assume that the sampling distribution is normally distributed, then we should use a parametric technique, which is what those techniques are designed for. And they're also stronger tests. We've talked about that several times. Parametric methods are stronger methods than non-parametric techniques. But if we can't assume normality, then we have to use a different approach, okay? And that approach, generally speaking, is a set of methods called nonparametric methods. There are several nonparametric methods that you can find in most any textbook. We've talked about one in particular for studying the median of a single population, and that's called the sign test. Okay, so the idea behind the sign test is that rather than, well, let's first talk about a parametric technique for the mean of a single population. Okay, so let's say we have a single population. We want to know if the mean is mu naught or if it's something other than mu naught. Okay, and we had a test statistic that said, well, let's go collect a y bar from a sample of size n and have a standard deviation s. And we have a test statistic that says how different in magnitude is y bar from that hypothesized value in standard deviation units. Okay, so that was our parametric approach for addressing this set of hypotheses whenever S is used in place of sigma. Okay, we have a t test here because we're using S in place of sigma. Okay, and so what we're dealing with here is the magnitude of difference between y bar, that sample evidence, and the hypothesized mean mu naught in standard deviation units. How different are those two things from each other? Okay. So if we can assume normality, this is the approach to use. Okay? If we can't assume normality, we can't even calculate y bar in the first place, right? If we have, for example, ordinal data, right? With ordinal data, for example, where we have a Likert scale, a series of answers to questions that are based on a Likert scale, 1 to 5, strongly agree or strongly disagree to strongly agree. Technically, with ordinal data, which is really what nonparametric techniques are designed for, you can't even calculate y bar in the first place because operations such as addition, subtraction, multiplication, division, they don't even work for ordinal data. Okay, so we can't even calculate a y bar to begin with. So if we're assuming non-normality, if we're assuming something other than normality, and we have to use a nonparametric technique, then this kind of approach doesn't work. Okay. So what does work? Well, first, we don't address hypotheses about means, we address hypotheses about medians. Okay? So here's our set of hypotheses for the sign test for a single population, the median of a single population. We're saying, is that median equal to some value, or is it not equal to some value? Okay? Where tau represents our median and tau naught represents that hypothesized median. Okay, and of course we could always have this situation or this situation. Okay, and so rather than deal with the magnitudes of difference between the median and the hypothesized median, we use something different. Okay, we count the deviations on one side of this hypothesized median and on the other. Okay, so we transform our observations y sub I into differences, okay, from on one side of this hypothesized median or the other, and we sum up the positive values or the negative values depending on what our hypotheses are. Okay, so if we want to know, is the median less than tau naught? If the median is less than tau naught, then we want to sum up how many observations are on the negative side to the left of tau naught. Okay? If we're asking in the alternative hypothesis, is tau greater than tau naught, then we want to add up the observations that provide positive deviations from tau, the observations that lie on the right side of tau naught. Okay? Or if we've got a two-tailed test, we want to choose what's larger, the positive deviations or the negative deviations. Okay? And the philosophy here is if we have a lot of observations on one side of tau or the other, then maybe tau really isn't on one side of tau naught or the other side of tau naught, then maybe tau naught really isn't the median. Maybe we should be rejecting the null, okay? Because you would imagine that if tau naught really is the median, we're going to have roughly half observations on one side and half the observations on the other side. If we see a significant difference from half on one side, half on the other, then maybe tau naught really isn't the median, okay? So this value S sums up these deviations that we want to look for, okay? Again, if we've got less than in the alternative, then we want to sum up the negative values of this difference for all I. If we've got greater than in the alternative, then we want to sum up the positive values for all I, okay? If we have not equal to, then S is going to represent the larger of the positive deviations or the negative deviations. Okay? So now we've got this value of S, the number of deviations on one side or the other of tau naught. And our test statistic is going to be, it's a z-test statistic, it's S minus 0.5 n divided by 0.5 times the square root of n. Okay? And where does this come from? This comes from the binomial distribution. We're assuming that observations on one side of tau or the other follow a binomial distribution. Or any individual observation is a Bernoulli trial. It either lies above the median or below. Okay? So S would measure the count of observations above or below. That would, S would follow a binomial distribution. So we want to know how different is S from the mean of a binomial distribution, which assumes that tau naught is the median. Okay, so the probability of lying above or below is 0.5. Okay, so how different is S from this expected value in standard deviation units? Okay, so that's the test statistic. It's a z-test statistic, and the approach from here on out is just the same as it's always been. Okay, we could use the critical value approach. For example, let's say we had a two-tailed test. We've got alpha over 2 in each tail. Okay, we can compare our test statistic. If it lies in here, if it lies in the non-rejection region, then the median is tau. If it lies out here, then the median is something other than tau, okay, with 1 minus alpha times 100% confidence. Okay, we could have a lower tail test or an upper tail test. Same approach still applies. Okay, this is the critical value approach. We could also use the p-value approach. Find the test statistic on the axis, look at the area in the tail. If it's a two-tailed test, multiply that area by 2 for a p-value. If it's a one-tail test, that area in the tail is just the p-value. Compare that to alpha and draw some kind of conclusions about whether or not to reject these hypotheses, the null hypothesis. Okay? So again, we're not looking at magnitudes. We are summing up the deviations on one side of the median or the other and comparing that to what we would expect if the median really was tau naught. And then that would follow a z-distribution based on the normal approximation of the binomial. And the same critical value or p-value approach still applies, same kind of concept as always, and then we make some kind of conclusion on the hypotheses.